Hello everyone, and welcome back to the molpigs podcast. Today we'll be talking with Yuan-Jyue Chen on two aspects of DNA data storage. Also with me today are Boya.
Hi.
Georgios.
Hello.
And I'm Will. Yuan is a senior researcher at Microsoft Research, as well as an affiliate professor in the Paul G. Allen School of Computer Science and Engineering at the University of Washington. His research focuses on DNA storage and DNA computing, and he collaborates closely with the Molecular Information Systems Lab at UW to make DNA storage a reality. Prior to Microsoft, he got his PhD in electrical engineering from UW in 2015, advised by Georg Selig, and in collaboration with MSR Cambridge and Caltech. He came to Microsoft Research as a postdoc in 2015 and became a researcher in the DNA storage group in 2017. Yuan, hi.
Hi, thank you for the introduction. Yeah, I'm very nice to talk to everyone here.
Yeah, thanks for coming. So, you've got a very interesting poster here on the development of efficient approaches to information retrieval in DNA data storage. Perhaps you could start with a brief overview of DNA data storage and the main ways people go about it.
Yeah, of course. So DNA data storage is the basic idea of storing digital information in DNA. So it typically kind of involves this kind of simple idea like you have the digital data, so you do some encoding to have some error correction codes first. And then you do chemical process to really convert this to molecules and store in DNA. And then of course we will develop some different methods to retrieve the data. After that you sequence it using sort of modern sequencing technology to retrieve sort of digital information stored in DNA, and then you can decode the data back. So that's kind of standard pipeline how DNA storage works.
Yeah, and so then kind of we're using standard technologies here, right? So PCR for the sequencing and regular synthesis, is that right?
Yeah. So in today's talk, we'll talk about like two different methods or we develop for like efficient search data. One's we kind of refer to random access, the other one we refer to like a similarity search.
Yeah, so tell us about the random access part.
Yeah, so the random access is kind of searching data based on their sort of data file ID. So the way it actually works is using a standard molecular sort of technique called PCR. So typically what we have is like a big data pool with like tons of information or files stored there. So what we do is like if you try to search a specific file, you'll throw in the primers corresponding to that file and then do the PCR amplification. So PCR will exponentially sort of amplify that target file. So once you do that, that target file should be like become the kind of quickly overwhelm the data pool. And then you can, once you sequence that, that becomes the only file retrieved there.
So when you're doing that, do you have any problems with kind of losing the original data in the storage? So presumably you'd take a small aliquot, but if you keep doing this, do you tend to lose some of the original information?
Yeah, that brings up actually the one of like our biggest research around this is while the method is really simple, but one sort of problem we kind of encounter is sometimes when you retrieve this data, certain sequences will kind of drop out on different files. So when we dig deeper into this, we found like the oligo distribution is sometimes very sort of unevenly distributed. What that means is like certain sequences are very underrepresented, so they are very easily to drop out. That cause some decoding problems.
Is that due to the sequence itself, or due to the actual differences in the primer that you're using between each file?
Oh yeah, that's a good question. So typically we don't observe from the primers sort of to cause this kind of problem. So we actually dig a lot deeper into this to each individual sort of molecular process related to DNA storage, what's actually causing this kind of problem. So the first process we dig really deep into is this called DNA synthesis. So one thing to kind of mention here is the synthesis for DNA storage. Typically we use this high throughput synthesis called like array-based synthesis. It's slightly different from column-based one. So it is kind of in the sense like you are synthesizing a lot of sequences at the same time. But one thing we found so intuitively you would think there should be sort of very evenly distributed, kind of nice, but what we found is this process actually can be very uneven. So the experiment we did there is like we make a pool directly from this array synthesis, and then we directly sequence that without any sort of molecular process in between. And then we map the sequencing reads back to the synthesis chip location. So what we found is actually very interesting. The certain location on the chip has like way much more copy number, and certain locations are just way much lower. If you look at like we have this paper published in Nature Communication like 2 years ago, you can see a very specific pattern on the chip. So we kind of, this chip, we kind of collaborate with Twist Bioscience. They use this technology called inkjet. So it's like a printing head technology to print nucleotides on different locations. And when they see this kind of map, they came back to them, they know immediately there's probably some kind of fluidics operation, so not very evenly operated to cause all these troubles. So they quickly kind of adjust their manufacture and then remake the same sort of sequence for us, and then we sequence them. Then quickly we found this is a lot more even.
That's really interesting. Is it what does the pattern of different representation look like? Is it a simple one where you get more representation in the center of the chip than at the edges, or does it have some other more intricate type of structure, like every other oligo is less represented?
Yeah, it doesn't really seem to be related to the oligo sequences itself. Actually, the pattern looks more like kind of like a stripe, much kind of a stripe more and then a stripe lower, a stripe more, a stripe lower. We don't really know what particular kind of device they use for that, but our guess is probably some sort of fluidic or printer head has an uneven kind of fluidic control initially.
Yeah. So now that you've collaborated with them a bit more, how much evenness have you been able to get? Is it a lot more suitable now for synthesizing for DNA storage?
Yeah. After that becomes a lot more even. So we have this kind of theory developed around this, like a standard sort of process, you should see a lot more like normal distribution. So after they're adjusting, that can become fitted really well to a normal distribution curve.
For the technique that you described, how long is the sequence that you can synthesize for one strand of DNA, and how is that related to the size of the file that you want to store?
Yeah, so we usually operate sort of synthesize the oligo around 150, but I think now they probably can push it to over 200 or even 300 bases using this chemical synthesis process. So in terms of like the file storing, how this kind of relates to, it's typically it's like the longer the sequences they can make, the more information you can store in one strand. So that kind of helps, because if you recall, like one thing we didn't mention specifically here is like we have sort of primers on both ends of the strand. So kind of like that kind of took out some information. So if you can extend it from 150 to 300, your information amount kind of double or even more than that. But this kind of levels of when you have a really, really long sequence, the information amount is not necessarily a lot better than if you have a lot more sequence. So there is some kind of like compromise in between.
And is that compromise because of the chance of errors and having to put in error correcting codes to compensate for that?
Yeah. So yeah, but more practically, I think currently it's just chemical synthesis. They have this kind of carbonate efficiency, so it's kind of exponential decay when you have longer and longer sequences. So just in practice, I don't think they really can do like 500 or something. Still in practice currently difficult.
And if a file is split across multiple sequences, does each file get its own individual primer? Like, is the primer itself the kind of unique molecular identifier for that file, or do you have to put in a bunch of different primers maybe for each file?
Yeah, for now it's like we have each file has like individual primers to identify. Yeah.
What's the how many different distinct primers can you get here when you're taking into account sequence orthogonality in the PCR process?
Right. So that's a good question. So we kind of design this primer using sort of like heuristic rules based on other sort of primer design. The majority of it is trying to reduce sort of like primer cross interaction. The pool, so we currently have like a couple of thousands of primers in the library, but we kind of did an estimation if you just have the whole 20 bases as primer sequence to do the kind of extrapolation. I think it can be like, I don't remember the exact number, but I think maybe like 100,000 or tens of thousands of like primer pairs you can make. Yeah.
And is it possible to increase data density if you run out of primers by by taking files that exist on multiple strands and ligating those to be one long strand, then indexed by one single primer, and then do one long high fidelity PCR for that one file?
Yeah, that could be an interesting like idea. Like you can kind of group things together. Yeah, so that could be one possible way. So there are actually some papers right now, I think people call it like hierarchical addressing. So the original paper we use here is like we have each file corresponding to a pair of primers, but potentially you could imagine like the primers actually can be sort of reused on both forward and reverse side. Just each file has a specific kind of pair. Yeah. So that could be like an exponential way to increasing one. So we are actually doing one research along this line too. So instead of like every file has a unique forward and reverse primer, we just have the forward primers can be sort of reused on different files, but the reverse can also be reused. But you can have, as long as it's a unique pair, then you could have exponentials or increasing on the files you need to store.
And because a file is split into multiple oligos, each of which have the same primer, do you get issues with because each oligo is being exponentially amplified? Do small differences in the initial amount of amplification, say due to tiny differences in the speed of the polymerase across different parts of the file, do they amplify so that you get weird different distributions of the file of the file structure in your final mix?
Yeah. That's also the second sort of biggest source we found in sort of like the bias comes from. We call like a PCR stochasticity. So it's exactly what you say. If you kind of store DNA, very very low copy number, of course you get a good sort of storing density. But the problem is PCR is an exponential process. So if a small variation in the initial amplification process, you can create a way much worse sort of distribution later. So that's also, we have done this experiment. We try like different copy numbers. So the lower copy number you kind of starting with PCR, the more significant this problem you can see.
So yeah, leading on from that, in the process of using DNA storage long term, you might do reads every so often, and then you'd need to re-amplify the original part of DNA. Do you see increasing effects from PCR stochasticity in that? And even if you start with quite a high copy number, is there any way to ensure that you don't get further dropouts as you keep using this same volume, or do you need to occasionally resynthesize the entire volume from scratch?
Right, yeah. So I think there are sort of two ways might be able to address this. One is sort of DNA pool, you can, just like you said, you can easily copy, so making a lot more of it. The other way is like if eventually all the synthesis can drop to a low cost enough, maybe after a certain time you just resynthesize the whole thing. Yeah. So it kind of depends on how all these technologies moves on, but we do have like multiple different ways to address this.
And in your random access pipeline, the NGS, the next generation sequencing that you use, are you is it compatible with kind of any next gen sequencing, or is it or can you use, say, nanopore sequencing or traditional next generation sequencing?
Yeah, so in the current pipeline we did here is just next generation sequencing from Illumina. It's the most sort of like mature technology at the current time. It can possibly change it to like nanopore sequencing. I think it's still like a random sampling process, but the potential issue is like for a nanopore, it may have like more trouble on readings or homopolymers or certain other ones. So if you want to put this into the model, you may want to have additional models to correct some of the particular errors in each particular device you're using or technology you're using. Yeah.
What are the timescales for this system? So how long does it take to prepare a DNA pool, and what are the current times for a random access?
Right, yeah. So actually this is very interesting. We actually did like a kind of DNA storage challenge. We try to finish the whole pipeline, including encoding, synthesis, PCR, kind of all this process. So potentially, I think we did show like it's possible to do within 24 hours. So the synthesis part, or Twist was able to push it to like within 8 hours, like around 8 hours each. And PCR actually is fairly fast. It's around 1 hour you can finish this part. But of course, it also relates to you have to prep there takes some time to prep for sequencing. So the library preparation, it takes actually multiple hours. So I think in that part, I think we also control to be within like 8 hours. And the sequencing part by itself, if we currently use in the next generation sequencing, it's like around 13 hours to 15 hours, depending on what kind of sequencer you're using.
And how large is the file for the computation you described?
That's a good question. I think we did probably around like 65,000 of strands. Yeah, but I don't remember if that's I think we tried a couple of different ones that might be very different ones. It shouldn't really matter too much. Yeah.
That's really cool. For the when you're doing the PCR, I presume you're not doing it by hand. I presume you've got like some sort of pipetting robot or liquid handling system. So does Microsoft build its own custom robotics, or do you just get like an off-the-shelf solution, or do you use one of those special Echo liquid handling systems to do is it on the microliter scale, or is it on the nanoliter scale that you're doing all this?
Yeah, currently we do this on a microliter scale. So we actually have like multiple automation pipeline. Originally, all these experiments were done manually, but now we have like two different pipelines to automate this. One is using the kind of open trunk process. So it's the robots. It's like an open resource. It's pretty nice. You can write a Python code, and it's pretty easy to code this thing. The other one we have is more like an in-house custom-made automation on this. One thing we call like a digital microfluidics. It's developed in Miso, so you have like droplets that can move along the digital microfluidics platform, so they can kind of merge. You can mix primers and then pick up certain pools. And the PCR part is still like under development. Yeah, for that platform.
Those are going back to the times, they're very impressive. So it definitely looks like it's coming along for a kind of cold storage technique. Do you think, can you envisage any big technological breakthroughs that might get it, say, under an hour, or more towards kind of warmer storage, if you could call it that?
Right. Yeah. So that kind of like depends on what kind of technology we use. So currently, I think if we can use, for example, nanopore sequencing, that could potentially give you like a real-time readout. So that could potentially drive this down to like, currently it's more like at least 1 day or so to do this process. But if you can do a real-time sequencing, especially nanopore it's like a portable device. Potentially you can read this like within an hour. I think it's totally possible. Yeah.
So what would you say the main lessons you've learned for random access are in terms of the bias and stochasticity?
Right. So we have like sort of two big discovery. One is like finding out the sort of bias. It could be related to your DNA synthesis and also your PCR stochasticity. And the other thing I think our biggest like find is like we developed this kind of computational model. So if you have some process similar to ours, you probably can plug those and play to give you a quick idea on how to optimize your process, like how much sequencing reads you want to use, how much PCR you want to do. So those I think are sort of pretty important to engineer kind of a robust system.
Is there kind of a time frame for the roadmap to making DNA storage a commonplace reality, that you might go to Amazon Web Services or whatever and get them to put it in DNA storage?
Oh yeah, this is kind of like, of course, everyone wants this to be as fast as possible. But currently, I think the biggest sort of bottleneck still lies on the synthesis cost. But the good news is like synthesis cost is also dropping quite quickly. Like, yeah, so hopefully more and more of this kind of array-based synthesis can be more material to drop this a lot further. Yeah, that will make this become more like in practice, more comparable to other sort of traditional technology. They may not be so dense, but they are really cheap.
So I recently learned that Microsoft Research is also developing another kind of high density cold storage system called Project Silica, where they aim to etch data into quartz glass using lasers. Is this kind of seen as a competition within Microsoft Research, kind of Silica versus DNA, or where do you think kind of DNA storage fits in the grand scheme of these new high density storage like kind of paradigm that we're entering?
Right. So here I want to just mention, like, I'm not representing Microsoft officially here, but as a researcher, I can try to provide my own opinion. I think it's more like a company could pursue like multiple threads. I think DNA storage has its kind of advantage in the sense like there are a lot with biotech technologies developing at the same time. So we could sort of potentially ride on the wave, like sequencing technology is going to be there as long as humans there. So all this technology will drive DNA storage a lot cheaper at a certain point.
Can you talk a little bit about the errors during either the synthesis process or the reading process?
Yeah. So in terms of errors, currently if we use like, for example, Illumina sequencing platform, they are really sort of low errors, like I think typically below 1%. But actually we found like synthesis, they are also improving a lot with time. So it depends on which technology you are using. The one we work with Twist, they are pretty high quality, but certain other sort of high throughput method could be more error prone. So this really depends on what kind of technology you're using. Yeah, and probably the most errors we have seen is typically the deletion errors. Just sequence could kind of drop out certain bases. But they are typically low enough that can be easily corrected using error correction codes.
Can you just use kind of standard error correction codes that we've known for decades, or do we need to develop new ones for DNA storage?
Yeah. So this one, I'm actually not an expert on the error correction codes, but in my general understanding is it's kind of adapting sort of the error correction codes we use for communication systems, but more like towards actual stuff we do here is a lot more like you have a lot of Kobe number sequences. You actually need to figure out how to use a lot of this kind of Kobe number information, but they could be a little bit different. But you also need to figure out how to make a consensus from that. And the other problem is you have a large number of sequences they don't have certain order. You need to clustering them. So the other researcher in our Microsoft have developed a very efficient they call like a clustering algorithm. So if people are interested, they can read more about those.
So you mentioned consensus. Is this Are the techniques very similar to those used in genetics and genomics to find consensus sequences in more biological domains? Or is this kind of a new type of consensus sequence algorithm?
Yeah, I think an intuitive way you could do is, for example, just a majority voting. But yeah, like I mentioned, I think the other researcher has a lot more deeper. He's like a theorist, so yeah, maybe reading the paper or asking this the other researcher called Sergey. He's a lot more knowledgeable than me on this question. Yeah.
And when it comes to kind of getting that consensus sequence, making sure you've got the most accurate possible readout, is most of your focus solely on kind of the pure DNA side of things, or have you do you guys also work on, or are thinking of working on kind of protein engineering to make more accurate polymerases to make sure that your amplicons remain as high fidelity as possible?
Right. So currently we're mostly working on just getting the sequencing reads as accurate as possible. The polymerase or errors, currently we don't think it's a big problem because on current technology, I think polymerase makes an error kind of 1 out of thousands of bases. They are way much lower than DNA synthesis errors, or even like if you use a nanopore sequencer, I think their error rate is probably more than 1%. So yeah, polymerase is not a main concern to us at this point.
So maybe now you could move on and tell us a bit about the similarity search part of the poster.
Yeah, so this is a research we think is really, really cool. So compared to the random access, this is kind of searching by content instead of ID. So one thing people may have done in typical search, for example, use Google image search or Bing image search, sometimes you don't really know what's the file ID you need. For example, if you try to find a cat that looks like your own cat, you may put in your cat image and then drag and drop into the search. They will find all these images for you. So our similarity search is kind of designed to do this kind of task.
Yeah, it sounds really exciting for kind of database applications. Is it analogous to kind of an index in a database to speed up the search through that? Or what would you compare it to?
Right. Yeah. So this particular one, I think our current ways of doing it is you probably store a bunch of images in their original sort of data store form, and then we kind of store sort of kind of higher level contents of the data in kind of index forms into this additional database. So the way we do it is we first take all these images and we do this thing called like feature extraction. So they are a little bit similar to like a high-level dimensions of each individual features based on the image contents. And once you have that, we train like a neural network that can convert sort of the high-level features into individual sequence, in the sense that if two images look similar to each other, they will have sort of similar sequences, so that they can have kind of better binding affinity if you have something trying to search along that.
And is the feature pre-designed or pre-encoded in the sequences, or you design sequences and somehow use neural network or something to learn and extract the feature?
No, the features is kind of just based on the images, so it doesn't. It's like.
Oh, sorry. I mean the sequences, the sequences that encode in those features. Do you design the sequences in the way that encodes the features, or?
Yeah. So the sequences basically you convert the features to sequences, but just trying to make sure like when the features are sort of similar to each other, you have sort of similar sequences. Does that make sense?
Mm-hmm.
Does the neural network part have anything to do with the feature extraction? I'm just wondering whether you have any of the adversarial edge cases where you can trick a neural network into thinking it's seeing a different image than it is. Like the ones where the 1 pixel attacks I'm kind of thinking of.
Yeah, so actually the neural network is trying to approximate like the binding affinity stuff. So I just want to bring up one thing. So this is actually a collaboration with like our a great student in at UW. It's called Kelly B. So she actually developed all these like computational pipelines. So I try my best to answer this, but yeah, just to give you guys a background. So the neural network actually is trying to figure out sort of the binding affinity of two sequences. I think if you work at DNA nanotechnology, you know, like typically we use something called like NuPack or MFOld to figure out how much binding affinity two sequences is. But the neural network here is kind of trying to approximate that process to make a model that can be sort of train those sequences for our purpose. Yeah, so it doesn't necessarily know what the features are meaning to them. They just try to make the process or making sequence have high affinity when features are similar.
Yeah, so you've got some graphs here which I think are kind of showing its fidelity and ability to specifically recall images by feature. Could you walk us through the quantitative results that you saw?
Oh yeah, of course. So I think the process we try to retrieve here actually shows like it has sort of different Euclidean distance between images. It's kind of showing how different image is. So if it's further away, of course you have a higher distance. And so the other y-axis we show here is the reads. So what this means, like if we do a similarity search and then you pull all these things out, and in this particular case, we try to use the axis of a read so we can kind of retrieve all the images. But the more similar images, you will get a much higher reads. So this gives us an advantage. So in the future, if like we show here, if they show very high amount of reads, then you can just use much lower reads to retrieve the similar images as we kind of demonstrate here. So the other one is more like we show it in a different way. So I think we are plotting here like the 100 nearest neighbors or images recall. So it kind of means like the most similar images. If you do search even using electronic computing, you know what 100 images are most closing to. And the y-axis here, we are showing how much proportion of the pool you actually need to retrieve to get that kind of amount of images out. For example, if we want to retrieve just the closest 10 images, do we need to retrieve all the 1.6 million images, or we only need to retrieve, for example, 1,000 images from that? So the lower amount of images you needed to do this, the more efficient it means.
And so did you say that as well as the feature sequences, do you also have a pool of the images encoded in DNA, and you can then do a kind of whole DNA process to so once you've found a similar image, how do you then go about retrieving the original image that is similar, if that makes sense?
Right, yeah. So that's a great question. So one thing I want to point out is actually the image you try to search doesn't necessarily need to be in the database. And so the way we do this is kind of like if you try to search one image, it actually goes through the same computational pipeline, kind of encode a sequence. So you first take that image going through like a feature extraction and then neural network to generate a sequence. But then the actual search probe DNA is the reverse complement of that. And then using that sequence, we kind of put it on a biotin. So this particular search probe will hybridize a lot better to images kind of closer to that. And then we use sort of magnetic beats trick to filter out all the similar images and throw away other not similar ones, just sequence the captured oligos.
So I have a question about how do you control the specificity for the query strand? How do you control that to make sure that it does not bind with other strands that you don't want?
Yeah, so that comes through more like the trick of the neural network. So the neural network is actually trying to train to make similar images with like very high sort of binding affinity. basically it's like driving. If you just have random sequences randomly encoded, every sequence probably has some arbitrary distribution of binding to each other, maybe more like normal distribution. But here we use a neural network to drive the more similar sequences to drive towards similar binding affinity very high, and then other not similar ones all driving to close to zero. So that's where even in the computational basis, we know this kind of gold standard sequence binding model that kind of help us to design a sequence in that sense. Yeah, and then our probe is basically just experimentally testing this, and the data actually we got is quite similar to the computational model prediction. Does that make sense?
Yeah.
Have you applied this to things other than images? Like, can you do the same with sound files and kind of anything with a perceptual part with that? Yeah, any kind of media. Does this apply?
Yeah. So that's like an open question. From my understanding, I think you should be able to do any sort of content similar. That should be able to do something like this way. But whether it's very efficient or not, it of course also depends on what kind of contents you are using. Yeah.
So are these 1.6 million sequences, or do you have multiple sequences per image? And do you generate these all with a single twist chip, or do you need multiple chips to build this kind of library size?
Yeah. So this one, we do using the twist chip, just one chip, they can make 1.6 million. So that's why we kind of determined to be this amount number. And in this case, we encode through each image into one single strand. That actually gives us about like 80 bases can encode this information. There are some other sort of nucleotides are encoded for kind of like a file image ID or other ones to specify which image you actually need to retrieve.
Did you experience any unexpected challenges in designing this system with Kali?
Right, yeah. So this actually is like experimentally we found is sometimes tricky, especially kind of like when you have this kind of magnetic beads extraction. I think it comes to like the molecular number when you have supposedly you want to have like a lower amount of DNA being stored, and then you can retrieve them really well. But one thing we found could potentially be difficult is like when you have very, very low oligo amount, there are certain sort of background always carrying through this process. Like it could be DNA binding to the tubes, binding to the beads, no matter how much you kind of extract it. So that kind of puts sort of like a practical constraint how much information or how much DNA you actually need to do this kind of search.
So is that like a constraint on the... So is it a constraint on just the copy number, also the concentration? Like if I wanted to search through 1 billion images, what would I need to change in this system to get that kind of specificity?
Right. Currently, we haven't like explored enough in terms of like scalability. We are trying to do those. But one thing we kind of tried experimentally on different concentrations. So clearly, I think a specific amount of copy number is definitely needed. We operated around 50 nanomolar. And yeah, I think the issue is like if you go lower, you're using lower bits, the actual information you retrieve is a lot lower, but there's a fixed amount background always coming through. So I think if you can have more images, in principle, this probably can still work.
This is sort of a bit tangential to the actual specifics about the content-based similarity search, but how interdisciplinary, because I see there's a long list of authors, how interdisciplinary is the team that you work with? Is it mainly kind of electrical engineers and computer scientists, or do you have molecular biologists, people from kind of more wet lab backgrounds as well? Or can everything be done?
Yeah. So our project actually involves a lot multidisciplinary. Like myself is a molecular biologist. So we also have like computer scientists as this project show like designing some of these neural network features. We also have electrical engineers to design sort of the automation systems, some chemists to help design some other process part, and also like statisticians to help us understand some of these like specific features about like biasing problems. So it's a very interesting problems involve a lot of different fields.
Do you notice any being part of both Microsoft and the University of Washington? Do you notice any big differences between working in those two environments?
Yeah, that's an interesting question. I think we actually build like a really good collaboration between these two. Typically, like UW, they have like can explore a lot of interesting problems that may or may not necessarily directly making the process like a little bit more robust or something, but they can try to develop other sort of new skills without too much worries. Like the other paper kind of MISO was doing is called like a molecular tagging system. So they develop like DNA can have like make easily barcodes they can read out very easily. So, but that has like shorter information stored there. But potentially you can sort of tag that on different system, and then you can easily retrieve that using a nanopore sequencer. Yeah. So those are like, I think at MISO, it's more like you can try a lot of different interesting problems. Yeah. And for us, we are also engineering towards more like making this more practical. So certain problems, like for example, the biasing problems, we are really interested to understand where this process is not very robust. Yeah. But I think we form like a really nice collaboration between these two. Yeah.
Yeah, it sounds like those two approaches complement each other quite well.
I have a question about how do you feel working in these two different UW versus Microsoft? Do you personally have any difference in regarding working environment?
Yeah. Actually, I like working in both, but working sort of initially to me, I was like a grad student, kind of like some of you guys are. So I kind of transitioned to Microsoft research as a postdoc first. So actually, I think it's really nice that kind of like Microsoft research is somewhat like an industry, but also gives you a lot of freedom to do all this kind of interesting research stuff. So it's a really niche kind of position, I think. And our project is still like very research oriented, so it's very kind of fun, and then give us a lot of freedom, even collaborate with all kinds of academic institutions to explore any kind of interesting topics we want. So I would say like this is a very nice experience I have and highly recommend.
And how, just like to get a sense of kind of how much in the way of resources are kind of being invested into this. How big is the team working on kind of DNA storage in Microsoft Research? Is it just in Redmond, Washington, or does it happen, say, here in Cambridge as well? Or is Microsoft Research constantly like kind of pumping more and more people into this, or is it kind of just steady at the moment?
So currently it's just we have like 4 core people like full-time working on this, but even in Microsoft, currently it's all at Microsoft Redmond here. We have like other researchers, they kind of also work on this, but they have their own other main projects. They help a lot. So in terms of the total team, it's actually a lot more people get involved. Yeah. And like I mentioned, actually, the MISO lab is a big kind of force for driving this project in different directions.
So yes, talking about kind of other people in Microsoft Research being able to come and join you, is that the kind of freedom that you have, that you kind of can choose for yourself what research you want to participate in, or what kind of structure is there to decide kind of what research activities you're going to do?
Right, yeah. So currently, my experience, like for example, DNA storage is our main direction. So we spend significant amount of time on those. But as a researcher, we also have the freedom to do other kind of interesting stuff that could become like a much longer sort of goal. Like I do a lot of DNA computing projects still, like some projects I didn't mention here. For example, we are driving some on like DNA-based neural network. So that could potentially drive so much longer term potential on different applications. So those ones, like, yeah, you probably spend less time on those, but those are still important stuff. So we collaborate a lot of those projects with MISO because they have students that can work on any kind of interesting problems.
Do you think you could at some point outsource the feature encoding into a DNA-based neural network?
That's kind of like the interesting problem we are trying to still explore. So one thing I guess for DNS technology is like what's like a cool application and but also practical. The similarity search is one thing we found kind of really kind of on this kind of interesting niche in between. You have tons of information stored and you can well use sort of highly parallelism to do computation. But in terms of like neural networks, some of this we are still trying to see like if there are some interesting problems. For example, if you try to identify certain features just in the molecular computation side, but it's still useful for like compared to electronic computation. Yeah. So those are like still open questions for all the experts like you guys, everyone to kind of explore.
Thank you so much for joining us, Yuan. It's exciting to see the progress DNA storage has been making recently. Perhaps DNA storage will be the first major application of molecular programming, and it certainly looks like it keeps maturing day by day. We'll be revealing details of our next podcast very soon. Stay tuned, and thanks for listening.